Okay, so let me go ahead and share the slides. I believe you can see the slides, so we'll continue. Today we're having our lecture 3 on ICH 311. Because basic raw material processing, chemical production based on natural gas and petroleum, production of raw materials based on natural gas and petroleum. I need to admit people. Okay. So, organic chemical industry has achieved great growth because of raw materials. Since inception of organic chemical industries, they have achieved great, tremendous growth since the 19th century. And the contributing factors that has helped in the achievement of this growth has been that of sustained raw materials that are needed in the industry. Without raw materials, there's no how any production can take place. And so most significant of the materials that have helped to sustain the industry is they're actually from the fossil source, petroleum and natural gas. Okay. So the preeminence of these natural resources as major sources of raw materials for organic chemical industry is universally acknowledged. And then these are the reasons for the sustenance of the raw material source. So one is that there's a huge world reserve that just give me so the reason for chemical industries being so well sustained can be attributed to these factors that I want to list for you now. I need to admit people. Okay. So one is the current world reserve that is claimed to be quite non-exhaustible, at least in the foreseeable future. So that is the reserve for petroleum and natural gas is much. And also, or the fact that they can be easily recovered and transported. That's another useful factor that is helping the chemical industry to grow because they are in liquid and gaseous form. So Another factor is that there's availability of proven technologies for processing them. Now, it is claimed that only 10% of these raw materials, of these resources, are used for production of organic chemicals. I've mentioned to you previously that 90% of crude oil that is drilled goes for production of fuels of different kinds. Only 10% goes for the processing of organic chemicals. So the petroleum industry started with successful drilling of first commercial oil in 1859. The first commercial oil well was drilled in 1859. And the opening of the first refinery 2 years later took place to process the crude into kerosene. That was what the crude was processed into initially, just kerosene. But now, today, petroleum refining is carried out, produce several other products like gasoline, fuel that we're using, kerosene, propane, fuel oil, lubricating oil, wax, and asphalt. So refining crude oil involves two kinds of processes, which I know I've told you before. The physical processes, and also the other one is the chemical processes. Physical processes, which is simply the refining of the crude oil without altering the structure of the compounds. So the crude oil is refined into useful products. Example is lubricating oil, fuel oil, and so on. That is a physical process that is involved in this. So the petroleum refining begins with distillation or fractionation, like what I've shown you in the previous lecture, which separates crude oil in atmospheric or vacuum distillation towers into different groups of hydrocarbon compounds that have different boiling ranges. And then such compounds are called fractions or cuts. So the second type of process is the chemical process. And we have several chemical conversion processes that alter the size and the molecular structure of the hydrocarbon molecules in order to produce a wide range of products. So it's not only kerosene like before. A wide range of products can be produced, in this case, from petroleum. So the processing of petroleum into natural gas and natural gas into primary petrochemical products, which are used as raw materials for downstream organic chemical manufacture, is the focus of the lecture today. So at the end of this lecture, you will know certain things. The aim of today's lecture is mainly petrochemical aspect of producing organic chemicals from crude oil. So you'll be able to know the main petrochemical processes for converting petroleum and natural gas into primary petrochemical products at the end of today. You will also know the varieties of derivatives of primary petrochemical products, and you also know their uses. Also, you will know other refinery processes that are used for improving the quality and yield of gasoline. In last lecture, we talked of octane number, And we'll see some of these processes that can help to boost octane number of gasoline today. So we'll start with treatment processes. When we have our crude oil, we have to start with the treatment first. Treatment processes are intended to prepare hydrocarbon streams for additional processing and to prepare the finished products. So you treat the crude oil first so as to prepare the hydrocarbons that you're going to use for subsequent processes that will lead to the preparation of finished products. So treatment may include removal or separation of aromatics and naphthenes, as well as impurities and undesirable contaminants. Of course, you remember I talked about sour and sweet crude oil. Of course, treatment also, you have to remove sulfur and so on. So treatment may involve chemical or physical separation, such as dissolving, absorption, or precipitation using a variety of a combination of processes, which also includes hydrodesulfurizing and sweetening. That means removing of sulfur from the crude before you start processing that crude. So another process also is formulating and blending, which is a process of mixing and combining hydrocarbon fractions, additives, and other components to produce finished products with specific performance properties. Combine different components of the hydrocarbon fractions to produce the desired whatever property you want. So integrated refineries incorporate fractionation, conversion, treatment, and blending operations. It may also include petrochemical processing. For instance, in Port Harcourt, we have the refinery and we have petrochemical industry. So maybe some people that are familiar with the refinery in Port Harcourt, I believe you will remember that we have section for refining and then the section that is called petrochemical. So the different activities take place there. So we're concentrating on the petrochemical aspect of it today, though we'll still touch some few things that link to octane number that will lead to just enhancing the refining products. Okay, so this is how the schematic representation of petroleum refining and conversion processes look like. So you can see here, you can also, when you get home, you take time and look at it properly, where your crude oil is coming in. First, when it comes in, it goes in for the fractionation, atmospheric distillation, and then from there you have gas that is released, the first fraction at low temperature. You have the gas there, goes to the gas plant, and then you have it passing into hydrofiner, and then you have the heavier ones coming down, then for hydrocracking to crack them into smaller compounds. And then you see how you get the fuel oil that is cracked into vacuum for vacuum distillation in this reactor here. And then, so you see on the right side, you see the different final products that come out from the process, the gas line, the kerosene, and so on. So you see everything there. So you can take time and go and study this schematic representation of the refining process. So raw material processing is what we want to look at based on petroleum and natural gas. So petroleum and natural gas can be processed by means of three main processes. And these processes are chemical conversion processes. One is thermal cracking, another one is catalytic reforming, another one is steam reforming. So we're going to look at these different chemical processes, and we will see what chemicals, what products they will give, and we'll also see what feedstocks that they need for the process. Okay. So we look at thermal cracking now. Thermal cracking of light hydrocarbon feedstock is a well-established petrochemical process. It is used for the production of light olefins, primarily ethylene and propylene. These are gases. So the feedstock also for this particular process, thermal cracking, the feedstock also gases. It can be either gases or liquid. The gaseous hydrocarbon, mainly ethane and propane, these are obtained from the natural gas. Sometimes also butanes can be used. These are the feedstocks. And then after processing, the products that we have are ethylene and propylene. Please give me 1 second. Okay, so we have the feedstock, like I mentioned, is gases, and then the products are also gases. Feedstock could be gas, or it could also be liquid hydrocarbon, those ones that are light with low carbon contents. So the gaseous hydrocarbons are usually ethane and propane, and sometimes butanes can also be used. Like I mentioned, they're obtained from natural gas. Liquid hydrocarbons also, mainly naphtha and gas oil, can also be used, and these ones are available from the fractions of crude oil primary distillation. I mentioned before, you can use crude oil for anything. You have to first of all carry out the fractional distillation. So the liquid hydrocarbons of low carbon content that are used in thermal cracking are those that are obtained from the fraction of crude oil fractionation. And then the gaseous feedstock are obtained directly from natural gas. Okay. So thermal cracking is a high temperature process. Of course, you can link it to the name. And it operates at temperature between 750 to 900 degrees centigrade. The choice of temperature is, however, largely determined by the ratio of ethylene to higher olefinic products desired. This means the temperature within that range that you choose is determined by a particular olefinic product that you are trying to produce from this method. So this method is a free radical process, and steam is used as diluent in the process. So because the process will continue repeating, joining the radicals to radicals, and so on, reactive chain carriers, keeping on to, to continue reacting, the different chain carriers continuing to reaction. So what to stop that is using that steam diluent. So the steam diluent produces a hydrocarbon partial pressure, therefore favoring initiation and beta scission reactions at the expense of termination. So it can terminate the reaction. So olefin yields are therefore favored by low hydrocarbon partial pressure. The actual steam diluent, the dilution level employed is detected by the type of feedstock and the cracking severity. The feedstock that you're using, remember, we can use either gaseous feedstock, that is from natural gas, or we can use some light oil from the cracking process. So depending on what feedstock you have, the dilution level will be determined by what feedstock you're using. It will also be determined by how much cracking you want to carry out, at the severity of the cracking process. So the steam dilution also helps to prevent tar formation by reducing the dew point of heavy products. It helps to prevent tar formation. As carbon formation, steam helps to dilute it. Carbon with the steam will produce gases instead of allowing the carbon to form. And so hydrocarbon dew point indicates the temperature at which heavy hydrocarbon components begin to condense out of the gaseous phase. Remember that the feedstock we're using, mainly the gases and light hydrocarbons. So there's a particular temperature at which heavy hydrocarbon compounds start forming during this process of thermal cracking. And so the steam dilution helps to reduce that temperature, which is called dew point. So hydrocarbon dew point. So steam dilution helps to reduce that temperature so that to discourage the formation of those heavier hydrocarbons. So when the gas is cooled at constant temperature, the steam, the heavy hydrocarbons keeps forming. So the steam dilution reduces that formation. So the hydrocarbon dew point, which is that temperature at which hydrocarbon of heavy, the heavy hydrocarbon components form, that is also called hydrocarbon liquid dropout. Either you call it hydrocarbon dew point or you call it hydrocarbon liquid dropout. And the steam dilution is what will help to lower this temperature, so that to lower this dew point so as to discourage the formation of those heavy hydrocarbon components. So higher hydrocarbon dew point normally indicate a higher portion of heavy hydrocarbon component. And this is an important parameter for pipeline operators. So if the natural gas contains high proportion of heavy hydrocarbons, there's a great risk of liquid condensate forming in the pipeline. So remember, what we're trying to form, the products we're trying to form are gases. We're trying to form gases, ethylene and propylene, not liquid. So, but if the heavy components are much, then the products will end up giving us what we are not looking for. So steam dilution further helps to render the thermal cracker coil surface passive and thus reducing potential coking. Coking there is a reformation of coke. So when you add the steam, it removes the coke via water-gas reaction. Water-gas reaction as we see here. So the coke will react with the steam and it will be removed in form of carbon monoxide and hydrogen. So the byproduct of thermal cracking may include methane, ethane, propane, and butane. And the thermal cracking is, however, not a major source of butadienes and aromatics. So although they can come out as byproducts, and it could be useful, but this thermal cracking process is not the major source of butadienes and aromatics. Major derivatives are ethylene and propylene, and you're going to see here in the next slide what we have from this ethylene and propylene. Major products that we have from thermal cracking are ethylene and propylene. So I'm trying to show you the different major derivatives from this ethylene and propylene. So from ethylene, if you pass it through, you carry out the reaction with oxygen or these other compounds, you lead chloride and so on, copper chloride, HCl, you will end up producing acetaldehyde. So it's either it's produced directly or in the presence of water, then you have indirect production of acetaldehyde. That is, you first of all, adding ethylene with your water, you have ethanol, and then removal of hydrogen from ethanol, you now get acetaldehyde. So it's either you get it directly or you get it from reaction with water. So also, you can get ethyl benzene also. And then removing hydrogen, you have styrene. And then from there, you can carry out polymerization of styrene to obtain your polystyrene rubber. So also, you can obtain vinyl acetate and then polymerize it to get your polymers. With HCl, you can get ethyl chloride, and then you get ethyl lead for improving and enhancing octane number from there. So for propylene, the second product that we obtain from thermal cracking, you have certain derivatives also. From your propylene, you can get polypropylene, through polymerization, and then you can get ethylene propylene rubbers, and then you can get acrylic fibers, you can get acrylic acid and acrylates, and then the polymers of it. You can get isopropanol, and then from there, just like we got ethanol from ethylene, and then removing water, you have acetonitrile. In this case of this propylene, you get isopropanol from it, reacting with water, and then removing the hydrogen, you get acetone. You can get phenol from propylene, you can get from there acetone, you can get polypropylene, and so on, polyesters, polyurethanes from propylene. So now you can get aryl chloride, you get glycerol from propylene also. These are different products you can obtain from propylene. Several chemical, organic raw materials. Okay, so now let's look at catalytic cracking. Remember, thermal cracking, we talked of just using high temperature and breaking down those molecules, the gas or the light oil, and then obtaining ethylene and propylene, and also obtaining some byproducts that also could be useful. And we have also talked of the different derivatives of the ethylene and the propylene. And we've talked, so now let's see the catalytic cracking. We'll see what are the feedstock for catalytic cracking and what are also the products for this. Usually the feedstock for this is vacuum distillate. We obtain this by vacuum distillation of atmospheric residue. That is, the first step of crude oil processing is atmospheric distillation. From that atmospheric distillation, you obtain, when you go back to the schematic representation I gave you, you will see that you obtain some atmospheric residue, which are heavier fraction of the crude oil distillation. Then you use the atmospheric residue, you use it for another kind of distillation that is called vacuum distillation. So what you get from that vacuum distillation is what is called vacuum distillate, and that is your feedstock that you're using for your catalytic cracking. So ethylene and propylene, they are the most important organic chemical feedstocks, which account for over 50 to 60% of all organic chemicals. And so this particular method, catalytic cracking, will also produce ethylene for us, because ethylenes are very reactive, so you cannot obtain them from natural gas. So for one to obtain ethylene, propylene, these olefins, we want to obtain them, one has to carry out these processes, either thermal cracking or catalytic cracking, to be able to obtain them, because you cannot find them existing naturally as along in natural gas because of their high reactivity. So definitely they have to be manufactured by cracking process, either thermal cracking or catalytic cracking. So the purpose of cracking is to break complex hydrocarbons into simpler molecules in order to increase the quality and the quantity of lighter, more desirable products and then decrease the amount of residuals. So the heavy hydrocarbon feedstock that I told you of, the vacuum distillate that we got, is cracked into lighter fractions like kerosene, gasoline, liquefied petroleum gas, heating oil, petrochemical feedstocks. So the LPG gases are feedstock for olefins, such as ethylene and propylene. So it means in the catalytic cracking, you will produce all what I've just listed, lighter fractions like kerosene, gasoline, the LPG, and then you now use the LPG as feedstock to produce the olefins like ethylene and propylene. So, of course, as you have seen, the catalytic cracking process is also producing fuel. So it means it's both petrochemical and a refining process. Catalytic process is both petrochemical and refining. Refining as producing fuel, petrochemical as producing feedstock. So the composition takes place by catalytic action on heating in the absence of oxygen. That's the process. Carry out the pyrolysis in the absence of oxygen. So the catalyst that is used in this case in a refinery cracking unit are zeolite, aluminum hydrosilicate, treated bentonite clay, fuller's earth, bauxite, and so on. So it's in the presence of a catalyst that you carry out catalytic cracking. Remember, in the thermal, it's just heating. So gasoline with low molecular weight is formed from heavy gas oil of high molecular weight. So we obtain gasoline also from this catalytic cracking process. Okay. There are three basic functions in the catalytic cracking process. One is that of reaction, the other one is regeneration of catalyst, and the other one is fractionation. The reaction is that the feedstock reacts with catalyst and cracks into different hydrocarbons. Of course, you know what a catalyst is. It's only hastening the rate of the reaction, it's not taking part in it. So you have to regenerate the catalyst. So the second function is regeneration of the catalyst and reactivating it by burning off the coal that must have settled on it during the process. And then you have reactivated catalyst that you put into the system again. Then the third aspect is fractionation, cracking the hydrocarbon stream and separating it into various products. So I've mentioned that primarily catalytic cracking is a refinery process, but it's also petrochemical. Primarily refinery, but also bring some other byproducts that are useful chemical raw materials. So why is it a refinery process? Because it increases the yield of gasoline components in the gasoline boiling range. So catalytic process is carried out at high temperature also, but not as high as that of thermal cracking. Remember the thermal one, we said 750 degrees centigrade to 900 degrees centigrade. No catalyst is used. But in this case, it's also high temperature, but not as high as that, 460 to 520 degrees centigrade at atmospheric pressure approximately. And during this process, several things can take place during catalytic cracking. Four major things can take place. One is that as these large molecules are being cracked, there is not enough hydrogen to go around all the small carbon compounds that are supposed to be formed. And so what happens is that there's not enough hydrogen carbon to go, hydrogen atoms to go around. Then there are some pure carbon atoms that get stuck together. So there are carbon atoms that do not have hydrogen. And so they just remain carbon atoms. So coke is formed. Then the second thing is that as the large molecules break up, there's a full range of smaller molecules from methane and up several smaller molecules, not a particular thing. Smaller ones are formed. Then due to deficiency of hydrogen, you will have a lot of olefin molecules also. Because when you're cracking big molecules, you end up, one thing that can happen, you end up with carbon, coke formed. And then another thing that can happen is that you have different ranges of compounds formed, from the very small ones to some other ones that are bigger, but lower than what you started with. And then the third thing is that if you have large molecules in the feed that are made up of several aromatic and naphthenic rings stuck together, then you will have smaller aromatic or naphthalic compounds plus some olefinic results. What that means is that if your feedstock, the heavy feedstock that you put in, has a lot of aromatic and naphthalic compounds, they will get stuck together. And then in the process of producing, you will have smaller aromatics, you have smaller naphthenic compounds that are broken down. And the fourth thing that can happen is that large molecules made up of several aromatic and naphthalic rings plus long side chains, they're likely to crack where the side chains are attached. And then the result is that, in short, sometimes you end up with very big, heavier molecules. So, and that are even very, very dense with low API. With low API, that is high density, high gravity. And so the API, I don't know whether it's in this class, it's American Petroleum Institute gravity. It's a measure of how light or how heavy petroleum liquid is when you are comparing with water. So if the API is high, then it means the petroleum is light. If the API is low, then the petroleum is heavy. It's ironically heavy. That's how it is. Okay. So now you have the gas cracker gasoline. Gas cracker gasoline as a liquid product of catalytic cracking is collectively known and produced together with substantial quantities of gaseous hydrocarbon. So, and these are called catalytic cracker gases as byproducts. So gases are also produced through this process, and the gases that you produce through this process are called catalytic cracker gas. These are byproducts from that you obtain. So this CCG consists mostly of propene and butenes, and you can recover this and use as petrochemical raw materials. The propene and butenes, which are the byproducts of catalytic process, can be recovered and used as petrochemical raw materials. So that is why we can term this particular process as both refinery and petrochemical, but primarily it's a refinery process, but has some byproducts that are petrochemical raw materials. So catalytic cracking only gives supplementary source of propene and butane. The traditional sources of such gases is merely the thermal cracking of gaseous and liquid hydrocarbons. So that of catalytic cracking is just a supplementary source. So the major derivatives of butenes, we have them here in this schematic presentation below. Well, this is just a cracker, catalytic cracker, where you can obtain your gasoline and you obtain catalytic cracked gases. So your butenes, these are the derivatives of the butenes. And you have the butadiene, you have the synthetic rubber, you have secondary butyl alcohol, you have methyl ethyl ketone, you have by polymerization of isobutene, you have butyl rubbers. Okay, so another chemical conversion process is the steam reforming process. It involves the reaction of hydrocarbon feed with steam at very high temperatures and also with catalyst. So this one, you put in your feedstock and you add steam along with it. You carry it out at temperatures between 800 degrees centigrade and 1000 degrees centigrade. And you still use catalyst, in this case, nickel catalyst. So the process affords primarily synthesis gas. This means the product that we expect from this steam reforming is synthesis gas. Synthesis gas is a combination of carbon monoxide and hydrogen. It's a mixture of carbon monoxide and hydrogen, and it's very useful for the production of several organic chemicals. So the feedstock for steam reforming may either be gaseous or liquid feedstock. Gaseous, example, methane from natural gas, or liquid like naphtha from petroleum refining. So, but methane is normally preferred to naphtha because it's very easy to process. The cost is not too high and it's not complex. The reaction is simple and the cost of operation is reasonable. Synthesis gas is of very great importance in the manufacture of ammonia and methanol. That is the combination, the mixture of carbon monoxide and hydrogen. So this gaseous mixture is a good source of hydrogen for hydrogenation process, and is also a raw material for oxo process. The first stage of the first stage of a two process for the production of straight chain alcohol. So the hydrogenation process you're carrying out, and then the oxo process is the first stage for the production of straight chain alcohol, as you can see here. So synthesis gas production by steam reforming is economically more attractive if you want to compare it to the other alternative routes via coal or coke. We have another method of producing synthesis gas via coal or coke, but that is not as profitable or economical as going through steam reforming to produce synthesis gas. So we have also a fourth one, which is catalytic reforming. You have amongst the chemical conversion processes, you have cracking processes and you have reforming processes. I've mentioned and I've gone through two cracking processes with you, the thermal cracking and the catalytic cracking. And amongst the reforming processes, we have the steam reforming, which we just completed, and then we have catalytic reforming. So steam reforming, as I've explained to you, as you have seen, is just producing synthesis gas. So, and synthesis gas is useful for the production of organic chemicals. So steam reforming is just a petrochemical process. Thermal cracking is just a petrochemical process. Catalytic cracking is basically primarily refinery process, but it also gives us some organic chemicals, and so somehow it's refinery and petrochemical process. So, and steam reforming is just petrochemical process. And catalytic reforming is both refinery and petrochemical process. So in the refinery, catalytic process is used to improve the octane number of light distillates for burning in modern high compression internal combustion engine. I took time and explained a lot about this burning and knocking of engine and the octane number thing to you in the last lecture. So the catalytic reforming process is the process that is used to improve the octane number of light distillates so that they will burn properly in a high compression internal engine without knocking the car engine. So as a petrochemical process, it is of great importance in the production of aromatic hydrocarbons, notably benzene, toluene, and...
Sorry, ma.
Yeah.
It's 5 o'clock and we have a class coming up next, ma. Sorry, ma.
Okay. I think
You've muted your mic, ma.
Oh, sorry. We're almost done. I was still talking of the catalytic reforming. So that is our last lecture for today. The catalytic reforming is the last lecture today. So, and you will get the link to the YouTube lecture, and then I will send this lecture as well to you. So, and I'm stopping here. And so you're free to go for your lecture.